Hi students, hearty welcome to the New Jyothi online classes on Standard 10 Chemistry. In this class, we are going to discuss about the first chapter, periodic table and electronic configuration. You are very familiar with this periodic table. This table has rows and columns. The horizontal rows are called periods and the vertical columns are called groups. There are 7 periods and 18 groups in the periodic table. So see, 118 elements extended from hydrogen to oganesson are filled in these 118 cells. This period is known as modern periodic table. This was put forward by Henry Moseley, an English scientist. What are the bases of modern periodic table? Look at the periodic table very closely. You can see the first element hydrogen, then helium, lithium, beryllium, boron, nitrogen, oxygen, fluorine, neon, sodium, and so on up to oganesson. Look at the atomic number of these elements. It is increasing one by one. So we can say that the basis of modern periodic table is the atomic number. Okay, we understand that atomic number is the basis of modern periodic table. Then why doesn't the element place in a particular position in the periodic table? Let us look at the sodium, position of sodium in the periodic table. It is in the first group and third period. Why can't you put sodium in any other group or periods? Say in second period or 8th group. Let us examine for the reason. Sodium has an atomic number 11. Its electronic configuration is, its shell electronic configuration is 281. So how many electrons are there in the valence shell? There is 1 electron in the valence shell. What's meant by valence shell? Valence shell is the outermost shell in which that electrons are taking part in chemical reaction. In the case of sodium, the valence shell contains only 1 electron. So sodium belongs to the first group. Look at the number of shells. How many shells are there in sodium atom? There are 3 shells, namely K shell, L shell and M shell. O, first shell, second shell and third shell. So altogether 3 shells are there. So sodium can be placed in the third period. That is why sodium is placed in the first group and third period. Look at the other elements in the first group. So lithium, sodium, potassium, rubidium, cesium, francium. All these elements are having a valence electron. That is why they are in the first group. Not only they are showing same properties. They are acting as very good metals. From this we can find that the number of electrons in the valence shell gives the group number, and the total number of the shells give the periodic number. So we can conclude that there is a relationship between electronic configuration and position of the elements in the modern periodic table. Now, what's meant by electronic configuration? It's nothing but the arrangement of electrons around the nucleus of an atom in various shells. According to Niels Bohr atom model, nucleus is the center of the atom, which contains positively charged protons and electrically neutral neutrons. In the case of hydrogen, there is no neutron, that you know that. Negatively charged electrons are revolving round the nucleus in various energy level called shells. The first shell nearer to the nucleus is called K shell, and second is called L shell, and the third is called M shell, and the fourth one is known as N shell, and it is going on like that. So look at the Niels Bohr atom model. Nucleus is having a positive charge. From the nucleus, the first shell is K shell. In that shell, there is an electron which is having the less energy, but it is more bound to the nucleus. So it is nearer to the nucleus, so the force of attraction between nucleus and this electron is greater. So going away from this nucleus, K shell, N shell, M shell, N shell, the force of attraction is decreasing. So the energy of that electrons in the outermost shell is greater. Precisely, we can conclude that as the distance from the nucleus increases, the energy of the electron in the shell increases and the force of attraction decreases. We know that the maximum capacity to accommodate electrons in a shell is 2n squared, where n is the shell number. Look at the table. So n values are given there. 1, 2, 3, 4. The corresponding shells are, names of the shells are K shell, L shell, M shell and N shell. The first shell, that is, its n value is 1. It is nothing but K shell. The maximum capacity of that shell is equal to 2 into 1 squared, that is equal to 2. Second shell, L shell, can contain 2 into 2 squared electrons, that is 8 electrons. Third shell is the M shell, which contains 18 electrons, that can be determined by 2n squared, that is 2 into 3 squared is equal to 18. Fourth shell, that is N shell, can accommodate 2 into 4 squared, that is equal to 32 electrons. Let us complete the electronic configuration of the elements from atomic number 1 to 20. Atomic number 1, hydrogen, it's having only one shell, that's K shell. K shell contains only one electron. Atomic number 2, helium, it's having 2 electrons. Both the electrons are going into the first shell. That is the maximum capacity of K shell. Atomic number 3, lithium, there are 3 electrons. The first 2 electrons goes to K shell and the valence electron is going to the L shell. So in the case of beryllium, atomic number 4, K shell contains 2 and L shell contains 2. The maximum capacity of L shell is 8. So the number of electrons accommodate from 3 to 10. You can see that 10 is neon. It is having an electronic configuration 2,8. So whereas coming to the next one, magnesium, of course, the maximum capacity of L shell is complete at 8. So it is going to the M shell. So the M shell is having a capacity of 2 into 3 squared, that is 18. So you can see that sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. Up to argon, 8 electrons are filled. That is atomic number 18, argon, is having an electronic configuration 288. Look at the variation in 19, atomic number 19. Potassium. Its electronic configuration is 2881. Up to argon, the maximum capacity to accommodate electron is obeyed by your equation 2n squared. But in the case of potassium, last electron goes to 4th shell, that is N shell. A major question here arises is, why does the last electron of potassium go to 4th or N shell instead of 3rd or M shell? Though the maximum capacity of M shell, that is 3rd energy level, is 18 electrons. After filling 8 electrons in M shell, next electron goes to N shell. This is the limitation of Bohr atom model. So this can be explained by introducing subdivision of energy levels or shells. That means energy level, major energy levels can be divided into sub-energy levels. That is, energy level or shells can be divided into sub-energy levels or subshells. These subshells are named as S, P, D and F. All shells are having subshells. First shell or K shell is having one subshell named as 1s. Second or L subshell, second or L shell having 2 subshells, that is S and P, named as 2s and 2p. Third or M shell is having 3 subshells, S, P and D, named as 3s, 3p and 3d. Fourth or N shell having 4 subshells, S, P, D and F, named as 4s, 4p, 4d, and 8f. What is the maximum number of electrons that can be accommodated in these subshells? Yes, subshell can accommodate 2 electrons, P can 6, and D subshell can accommodate 10, and F can accommodate 14. So how to fill electrons in the subshells? We know that the electrons are filled in the shells in the increasing order of their energy. That is K shell, L shell, M shell, and N shell. Similarly, electrons are filled in the subshells in the increasing order of the energy, that is S, P, D, then F. Look at the increasing order of energy at various subshells. 1s, 2s, 2p, 3s, 3p, 3p, then not 3d, it is going to 4s. Then 3d, 4p, 5s, then it is going to 4d, then 5p, then 6s, and then only 4f. This can be easily remembered by using off-bow order. So look at the picture. That is, the order is maintained as such. First row you can see 1s, second row 2s, 2p, third row 3s, 3p, 3d, and it is the order of filling electrons in the subshells. So using this, how to write the subshell-wise electronic configuration of elements? Let us write subshell electronic configuration of hydrogen. So that we require the atomic number of hydrogen. It is 1. So hydrogen is having only 1 electron, because atomic number is equal to the number of protons. Or you can say that atomic number is the number of electrons in a neutral atom. Neutral means the number of protons and electrons are same. So they are electrically neutrals. Or otherwise, that is why atoms are electrically neutral. We know that the electrons in the K shell is having only one subshell, that is 1s. S subshell can accommodate 2 electrons, but in hydrogen there is only 1 electron. So it can be accommodated in 1s and can be represented as 1s1. It is read as 1s1. So write the subshell electronic configuration of helium. Atomic number 2. So there are 2 electrons in the atom. The electron configuration is 1s2, read as 1s2. When we write the subshell electronic configuration, the number of left side of the subshell denotes the shell number. That is, in 1s2, 1 denotes the shell number. The number on the top right side denotes the number of electrons in that subshell. So in the case of 1s2, 2 is the number denotes the electrons in that shell. Look at the table. In this table, argon is having atomic number 18. Its subshell electronic configuration is 1s2, 2s2, 2p6, 3s2 and 3p6. Its shell configuration is 2, 8, 8. So no problem. So far no problem regarding writing the electronic configurations, both subshell as well as shell-wise electronic configuration. Coming to the electronic configuration of potassium, it is having atomic number 19. 1s2, 2s2, 2p6, 3s2, 3p6 and then it is 4s1. So, its shell-wise electronic configuration is 2881. So, based on that, we can write the subshell electronic configuration by knowing the increasing order of energies of the subshells. That is 1s, 2s, 2p, 3s, 3p, 4s, then 3d, 4p, 5s, 4d, 5p, 6s and 4s. 6s and 4f. In potassium, there are 19 electrons. First shell contains 2 electrons, so the subshell can be denoted as 1s2. Second shell contains 8 electrons, so the next 2 subshells can be represented as 2s2, 2p6. Third shell contains 8 electrons, so the next 3 subshells can be represented as 3s2, 3p6, 3d10. So the energy level of 4s is less than that of 3d. So the next electron goes to the lowest sub-energy level 4s, not in 3d. Fourth shell contains 1 electron, so it goes to 4s2. Fourth shell contains 1 electron, so it goes to 4s1. Thus, the subshell-wise electronic configuration of potassium is 1s2, 2s2, 2p6, 3s2, 3p6 and 4s1. Let us write the subshell-wise electronic configuration of calcium. Its atomic number is 20. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Write the subshell-wise electronic configuration of scandium. Scandium is having atomic number 21. So, the shell-wise electronic configuration can be represented as 2, 8, 9, 2. The electrons are filled in the order 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and then 3d1. But the subshell-wise electronic configuration can be written as 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2 in the order of the shells. Writing the subshell electronic configuration of elements with a high atomic number, the symbol of the noble gas proceeds. Writing the subshell-wise electronic configuration of elements with a high atomic number, the symbol of the noble gas proceedings to the element may be shown in the square brackets followed by the remaining electronic configuration. Have a look. Scandium, atomic number 21, can be written as 1s2, 2s2, 2p6, 3s2, 3p6, 3d1 and 4s2. So this can be abridged, right, in the shortened form. Scandium, so in the square bracket argon is written, and then 3d1, 4s2. The electronic configuration of argon is 1s2, 2s2, 2p6, 3s2 and 3p6. So similarly, we can write the subshell-wise electronic configuration of the following elements: scandium, titanium, vanadium, manganese, iron, cobalt, nickel and zinc. Now write the electronic configuration of chromium. Chromium is having an atomic number 24. So it can be written as 1s2, 2s2, 2p6, 3s2, 3p6, 3d4, 4s2. But this is not the stable electronic configuration of chromium. The stable electronic configuration of chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5 and 4s1. Look at one electron from 4s is shifted to 3d and become 3d, 4 become 3d5. What is the reason for this? D subshell can accommodate a maximum of 10 electrons. The completely filled electronic configuration of D, that is D10, or half-filled electronic configuration, that is D5, is more stable than partially filled subshells. Based on this, atoms with D4s2 can be changed into D5s1 and D5s1 and D10s1 are more stable than partially filled subshells. Similarly, F7 and F14 are more stable than partially filled F subshells. Next, find the electronic configuration of copper. Copper is having an atomic number 29. Say its subshell-wise electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10 and 4s1. Actually 3d9, 4s2, but the stable form is 3d10, 4s1. You may be knowing the reason, because completely filled subshells are more stable than partially filled subshells. Now, let us discuss a question. Electronic configuration of atom is 1s2, 2s2, 2p6, 3s2. Answer the following questions. How many shells are present in this atom? 1s2, 2s2, 2p6, 3s2. So 3 shells. This can be found by knowing the highest shell number, that is 3. So there are 3 shells. Which are the subshells of each shell? There are 3 shells. First shell or K shell contains one subshell, that is 1s. Second shell contains 2 subshells, 2s and 2p. Third subshell contains one subshell, 3s. Which is the subshell to which the last electron was added? Last electron is added to 3s. What is the total number of electrons in the atom? 2 plus 2 plus 6 plus 2 is equal to 12. That is 1s2 having 2 electrons, 2s2 is having 2 electrons, 2p6 is having 6 electrons, and 3s2 is having 2 electrons. So altogether 12 electrons. So atomic number of this element is 12. How can the subshell electronic configuration be written in short form? So we know the electronic configuration as 1s2, 2s2, 2p6, 3s2. The preceding noble gas is neon. Its electronic configuration is 1s2, 2s2, 2p6. So it can be written as, in the square bracket neon, then 3s2. These types of questions and advanced type of questions are available in New Jyothi SSLC rank file.